The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm Rachelle Saunders, back in the guest hosting chair again and standing in for regular host Desiree Schell. Today I'm here with Carsten Krauss, an assistant professor and particle physicist at the University of Alberta in Edmonton. His work has taken him 2 kilometers underground to the Sudbury Neutrino Observatory that has produced insights into the properties of neutrinos and provided new information about the core of our sun. He is working with a team at the newly opened Snow Lab extension of SNO on the Picasso Dark Matter Search Experiment. Welcome to the show, Carsten.
Thank you very much.
So I think the best place to start is with a little history on the dark matter theory. Given how cutting-edge dark matter research is, I was actually kind of surprised to learn that the theory has been around since the 1930s.
It's one of the most long-standing problems in physics. I'm not a physics historian, but I think there are not a lot of problems that have been of fundamental nature that have not been solved in a long time. And so the first indication that there is something wrong or not understood came in 1934 when Fritz Zwicky looked at the rotational behavior of the Coma cluster, and he found that the mass that he saw and the dynamics that he was observing just don't match up. And ever since, we have collected more and more evidence with more and more sophisticated techniques, and really the puzzle hasn't gone away. And that's why nowadays everyone believes that there is something out there that could be dark matter, and of course we're trying to find out what it is. There has been a shift in terms of initially it was just solving a problem, and now we believe there is dark matter, but we haven't actually figured out what it is.
So what observations originally led to the theory of dark matter? You talked a little bit about something not meshing with the rotation of how fast galaxies were moving?
In the 30s, of course, the telescopes that they had were a lot less sophisticated than the instruments that we have at our disposals today. And so they were not able to look at individual galaxies and the movement of the galaxies. They had to look at galaxy clusters. Galaxy clusters they behave to galaxies like the solar system, or the galaxy behaves to the solar system. So they're just one order of magnitude up in terms of the overall structure of the universe.
Okay.
So lots of galaxies form clusters. So the galaxies themselves are not evenly distributed among the universe. They come in bunches, right? And so the Coma cluster is one of the first ones that was identified like that. It's one of the best studied because it's relatively close. And he studied the redshift of each of these galaxies within the cluster, and he found that they are moving in a way that doesn't match with the amount of mass that they had to assume based on the number of suns that were in those galaxies, the number of stars that were in those galaxies. And so that was the initial, or that's what we nowadays assume to be the start of the search for dark matter. But back in the days, although Zwicky was a very well-regarded scientist who had lots of great ideas and lots of contributions, this discovery of what we now know as dark matter wasn't really taken seriously for a very long time. One of the reasons was that there was just no way to verify it with the technology of the day.
Right.
And so it took all the way until the late 60s, early 70s, when a woman by the name of Vera Rubin measured the rotational curves of galaxies. So now that means she went one whole step down in the distribution of matter throughout the universe. She went from galaxy clusters, which was the smallest object that Zwicky could observe in the 30s, and then in the late 60s, early 70s, she had the ability to actually resolve the movement of galaxies individually. So if you imagine the Milky Way with its spiral arms, So she would look at galaxies where she could see a part of the galaxy moving towards us and another part of the galaxy moving away from us. And that you can see in the redshift of the individual stars. Stars, say, if the left part is moving towards us, stars on the left would be redshifted more than the stars on the right, which would be redshifted less. And that allows you to give a velocity distribution of both stars. And she could actually measure a function as to what the velocity is in relation to the distance from the center of each galaxy. And she found that they just don't match up. They are by far too fast. The stars that are far away from the core of the galaxy are moving a lot faster than predicted just by gravity. And that could mean two things. It could mean that gravity is completely wrong.
Right.
Either it's different out there, or the stars are not somehow attracted the same way, or there is more matter hiding somewhere, meaning more mass hiding somewhere further out from the galaxies that would speed up all those stars that are a little bit further away from the core of the galaxies. And at that point, people started taking it seriously. Not initially. They thought this new method that she developed was just not up to speed. But in fact, it was, and it got better and better with new technology. And other people started doing the same measurement, repeating this, and they all got the same results. There's almost no galaxy out there that does not behave that way. So basically, if you want to put it in simple terms, all the stars that are pretty far away from the cores of their respective galaxies are breaking the speed limit. They're way too fast compared to what they would be allowed to by gravity alone.
My understanding is that galaxies are basically spinning so fast that they should be kind of pulling themselves apart. Is that correct?
There is something that is pulling these stars out, and that's what makes them move faster. But it is not visible. It cannot be seen with a telescope. And that's obviously why people started calling this assumed mass that would do this for us, that would fix all the laws of physics as we know and love them.
Right.
We call it dark matter just because it is invisible. And it really what it does, it codifies our ignorance about what really is the fact about this. So we really don't know a lot about it. We can infer where it is and how much it is and how it behaves, but we don't really know what it is. So, and that's obviously something that, as experimentalists and as scientists, that's irking us a lot, right? That's what's keeping us awake at night. We want to find out.
Right.
What that is.
So how exactly do we estimate the actual mass of galaxies we can only see through telescopes? The dark matter mystery is primarily a numbers game. So how do we understand what the mass is of these galaxies?
So there are several ways of assessing the mass of a galaxy. The initial way that even Zwicky was able to do is you just basically check how much light you see. Okay, so you have a certain measurement instrument, and you know how sensitive it is to light, and you know how far the galaxy is away, and how large it is, and then you measure the amount of light that comes into your instrument for a given amount of time, and that tells you how much light you saw. And because most stars give the amount of light that comes off the star is proportional to the mass of the star. So if you see a certain amount of light, you see, okay, well, this has got to be this many stars, and they're probably this heavy. And so this is a very good way of being able to say, I have, say, a certain amount of light, and that allows me to infer that there has to have been a certain amount of mass in the stars.
Okay.
And that's how we basically weigh galaxies. It's a little bit indirect, and it's not. It is not free of mistakes because, of course, there could be dust in the way between the galaxy and us.
Right.
That dust absorbs light. Then you lose some, and you're going to make a mistake in the weighing of the galaxy. On the other hand, you can correct for that if you know that there's a certain amount of gas there.
Okay.
So that is the standard way of determining how large a galaxy is.
You're listening to Skeptically Speaking with Rachelle Saunders, and today we're exploring the mysterious world of dark matter with Carsten Krauss, particle physicist and assistant professor at the University of Alberta, and an experimentalist working on the Picasso experiment at the new underground snow lab in Ontario. Now, my understanding is that dark matter is pretty clumpy, with some galaxies having lots of it and some places having almost none at all. Why is that?
The exact answer is probably a little bit beyond my expertise, because I'm looking for the particles. I'm not particularly well versed with all the observational evidence that is there. But in some sense, what we now believe is that the dark matter that we see is actually what made the galaxies form in the first place.
Okay.
So in some sense, you would think, oh, well, the dark matter is where all the stars are, but it's just the other way around. The stars are where all the dark matter is. And it's easy to understand if you think about the scales. There's a lot more dark matter out there than there is stars and gas and normal material. And so the little bit of normal material that we have actually accumulated where all the dark matter is. And so there were small fluctuations in terms of how much dark matter was there initially at a given point in space. And these fluctuations are what enabled the formation of galaxies, galaxy clusters, and stars, because the matter would fall into the gravitational wells, into the places where there's a lot of dark matter initially, and that would in turn enable the stars to start burning. And so the fluctuations that we see between different galaxies are mostly primordial fluctuations, but of course it can also have something to do with the dynamics of a certain system. But then again, I have to admit that I'm not a big expert into why variations between dark matter density in different spots have been observed. But one of the things that has been observed and that people have been talking about a lot is the so-called bullet cluster. The bullet cluster is a very, very unique set of galaxies. It's two galaxies that have sometimes in the past, and if you talk about astronomical scales, actually relatively recently, these two galaxies have collided. And so in this particular case, we can see that the stars have been sticking to where the dark matter was. So the two galaxies went right through each other, and the dark matter didn't interact at all, because that's one of the key features of dark matter. It doesn't interact at all.
Okay.
And the stars also went through each other, because there's not a lot of them, in fact. Maybe a few would have collided, but the chances of that happening is relatively small. The only thing that did interact was the gas that is normally between galaxies. So there's actually a lot more mass. We didn't know that in the times of Zwicky in the 30s, but now we know that there's actually a lot more mass between stars in the form of gas than there is in the stars themselves. And this gas for this particular cluster was actually stripped from those two colliding galaxies. But the main amount of mass is still where the stars are. And that, again, is not because of the stars. The stars are actually lightweight compared to the dark matter. But we can see, because of a technique called gravitational lensing, that all the material, the mass has stayed where the initial galaxies were. They just passed through each other. And in this case, although there's a little bit of dynamic movement, I think the statement that I'm going to make is correct. I'm not 100% sure. But I think that mostly dark matter amounts are a result of the fluctuations that we saw from the initial universe. And so there's it's just basically a random fluctuation that makes dark matter appear a little bit more dense in one area and a little bit less dense in another area.
Okay. This actually segues really well into a question that I've received from the chat. From email. This is from Gina.
Was dark matter around from the Big Bang, or was it created later?
Yeah, that's a wonderful question. So we now believe that dark matter was around from the very beginning. Well, obviously, the exact dynamics of the Big Bang is still something that we need to know a little bit more about, because there's a limit as to how far back our knowledge extends, and that's because our accelerators on Earth have a limit in the amount of energy that they can reach, and so we can only go so far back time that is equivalent to the amount of energy that we have at our disposal. But the bottom line is that at a relatively early stage, just a few 100,000 years after the Big Bang, there certainly was dark matter around, and that is one of the strongest pieces of evidence that we have now that makes us believe that dark matter is around. And that is, so this evidence comes from the cosmic microwave background, and the best results so far come from a satellite experiment called WMAP that was launched by NASA a number of years ago. The predecessor to which, the COBE experiment, the principal investigators just won a Nobel Prize a few years ago. And there is now a European mission trying to get even better data out of the cosmic microwave background in order to find out if our theory needs to be revised, or if it's just fully understood already.
So if dark matter originated or came in around from the Big Bang, are experiments that are trying to replicate the circumstances of the Big Bang also looking for dark matter from those experiments?
Absolutely, yes. So that is one of the main motivations, in fact, of what is happening at CERN at the moment. If you hear about the experiments that happen at CERN in Geneva at the moment, you'll probably hear a lot about the Higgs boson because they haven't quite found it yet. They're probably pretty close, but they haven't announced anything yet. But the other big incentive for doing these experiments is trying to figure out if dark matter can be found or can be directly produced at one of these accelerators. So we believe, in fact, that the energy that we need to produce dark matter should not exceed the machines that we have at Geneva, the LHC machine in particular, by very much. And so we think that there's a very good chance that this machine will have the opportunity to produce these particles. However, since these particles don't interact very much, it is quite difficult to coax that out of the data that it happened.
So do you know if they've found anything that would be a good candidate for dark matter yet?
No, they have not found anything. So they have not made any major announcement in terms of new discoveries. And in some sense, we have to cut them a little bit of slack. They have a brand new machine, probably the most complicated machine that was ever built on this planet.
Right.
And it's just starting to work very well. And so I think it's not surprising that will take a little bit longer. And then, of course, also if you look at how to make a discovery, you don't just announce willy-nilly that you found something that you think is new. You actually want to be very certain before you announce something. So it's not only that the machine has to work properly and has to be understood properly, it's also that you just need to have enough evidence, and that sometimes takes time.
You're listening to Skeptically Speaking, hosted by Rachelle Saunders, and we'll be right back to discussing the theory of dark matter with particle physicist and University of Alberta Associate Professor Carsten Krauss after this.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com, or if you're on Twitter, tweet us at Skeptical Radio. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, here today with University of Alberta Associate Professor and Particle Physicist Carsten Krauss, dark matter expert and experimentalist. Today we're discussing the ongoing search for dark matter, the stuff that supposedly holds the galaxies together. Now, for all this dark matter theory that we have, the stuff has turned out to be extremely elusive during experiments. So why is that? Why has it been so hard to find?
Let me start by going back to the bullet cluster. So the bullet cluster is this cluster where two large clusters of galaxies have passed through each other, and we have observed that the two galaxies have not interacted, and more importantly, that the dark matter that surrounds these two galaxies has not interacted. And what that tells you is that although there's a large amount of matter there, it just didn't interact when they were hitting each other. And in some way, I mean, there's nothing more massive in the world that we know than a galaxy cluster. In some way, this is like hitting two really heavy things head on, and they just passing through each other. Right? And so what that tells you is that there is a certain likelihood associated with dark matter interacting with each other, and that likelihood has to be very, very small. Otherwise, all the dark matter that was produced at the Big Bang would have annihilated already. So we assume that dark matter can not only speed up the stars, which was the first thing that we observed it does. We think that it can also annihilate with each other. And people have been searching for hints of this annihilation, and they have been searching for direct evidence of dark matter, but we just haven't found anything. And we don't really, we didn't really expect to see anything from the beginning, because we knew that the cross-section is extremely small. And what that means in normal terms is that the probability of the dark matter interacting with anything that we can put our hands on is just incredibly tiny. And that's why we haven't seen anything.
So how long have experiments searching for dark matter actually been running?
Oh, that's a great question. I just saw a talk this week that showed a historic overview of this, and I think people have been using experimental data to interpret dark matter properties ever since the late 70s. So basically, right after people started believing in dark matter and in the existence of dark matter, people have been starting to search for it, and they always had to use the most sophisticated, most sensitive methods to detect interactions with particles. And back then, that was probably very similar to what we use today. That was germanium detectors, but the detectors back then were incredibly tiny compared to what we can build today, and they were also incredibly noisy compared to what we can build today. So the limits back then were of course not very stringent, and in some sense, even based on the theory, because we do expect the dark matter particles to be interacting only very, very weakly, we wouldn't really expect dark matter to have been found any time before now, because only now we really have the means at our disposal to do that kind of measurement. And the things that we need to do that measurement is, first of all, a very sensitive detector with a very low background. And in order to achieve that very low background, we need a laboratory that is deep underground. And that's something that people just didn't have back then, because the need for having such a laboratory just wasn't there before. So only with the advent of neutrino physics on the large scale, these laboratories were built, and now can also be used for dark matter searches. And that, of course, is why SNOLAB was built. SNOLAB is the deep underground science laboratory that is in Sudbury, Ontario, that was just opened last week.
So why build these things? What's the importance of building these laboratories so deep underground? What is the requirement there?
Well, we scientists like to hide from the world, right?
Right, of course.
No, the real reason is that on the surface, there is a lot of radioactivity that is impossible to keep out of an experiment. And so in terms of finding dark matter, what we expect for some of the theories, for some of the more common theories where we expect to understand the likelihood of finding this, we expect to find in a detector that has a mass of 1 ton and that operates for a full year, we expect to find as little as just one event.
Wow.
And obviously, you want to be very certain that you don't miss that one event. And if you think about how much uranium and thorium you have in 1 gram of, say, clay sand or concrete, for that matter, that leads to billions and billions of decays in that 1 ton of material. If you would just use a material that is built from ordinary materials, and so obviously we wouldn't be able to pick out that one tiny signal from those billions of radioactive decays, many of which would deposit a lot more energy than the dark matter interaction that we're looking for. And therefore we want to make sure that we stay away from all of these background decays.
So it's basically a way to limit the number of distractions you have to kind of filter out.
Exactly. It's much easier to find a needle in a tiny haystack than it is in a gigantic haystack.
That is a fantastic analogy. We have another question from the chat. This one's from Distempson.
Is neutrino mass a factor in understanding dark matter?
Neutrino mass was initially thought to be the answer for dark matter. People thought, neutrinos oscillate. Ever since the first ideas, Pontecorvo formulated the theory for neutrinos that oscillate, people thought, yes, if they oscillate, that means they do have mass, and if they have mass, that means they can be dark matter, because in some sense, neutrinos are perfect to explain dark matter. If they have mass, they would actually account for all that speeding up of stars.
Right.
If they would be impossible to observe because they also only interact weakly. Mm-hmm. But there is one problem with them. First of all, the amount of mass that we are looking for cannot be accounted for with the very, very small neutrino masses that we have observed. So that was a little bit of a letdown. But there's another problem. When you look at the formation of galaxies, this is an indirect problem, but nevertheless, if you start, say, at the Big Bang with just fluctuations in density of the dark matter that we have observed with the microwave background, we cannot arrive at today's universe if the dark matter moves very, very fast. Because if it moves too fast, it's not bound to itself and it doesn't actually conserve its structures. And I just told you that we have observed all these large structures, galaxy clusters, galaxies, and all of which form around these dark matter incubators for stars. And if dark matter would move very, very fast, there would have been a completely different dynamics in the formation of stars and galaxies and galaxy clusters, and our universe would look entirely different.
Okay.
In fact, people have tried, and they have not succeeded to make a universe that looks anywhere close to ours with fast-moving dark matter. However, if you assume that the dark matter moves very, very slowly, it all works beautifully. The universe that you simulate that way looks exactly like ours. And so this is a pretty strong hint that neutrinos cannot be a big factor in dark matter. And that's for the two reasons that I stated. First, the amount of mass that neutrinos bring to the table is just not sufficient, and they behave very differently in terms of the amount of velocity that they have. So their dynamics is entirely contradictory to the observations that we have made.
So I'd like to talk a little bit about weakly interacting massive particles, which, by the way, WIMPs is one of my favorite acronyms ever. It sounds like some of the experimental detectors are finding these particles and some are coming up completely empty.
Yeah, that is the status right now. We would actually really like to understand the picture ourselves. But at the moment, let me just describe the pictures for those that are not that familiar with this. What we do right now is we have developed several different techniques that search for dark matter. And some of these techniques have been around for a while, some are brand new, and all of them are pushing harder and harder, further and further to try to find dark matter. But in reality, none of these experiments, with the exception of maybe one, has any conclusive evidence to show. All of these are very, very marginal results, and they, as such, cannot be taken as evidence for dark matter. They can be taken as a hint or something like that, but they're not very strong.
Okay.
And they all contradict each other. And the best experiments, in fact, exclude pretty much all of them. And so there is obviously a problem here. A lot of contradictory results, and to the uninitiated, it looks like we're not knowing what we're doing. But I would like to maintain that we actually do know what we're doing. But that right now, it's just at a stage where we either have to overcome a new background that we have never measured before because we never had instruments that were that sensitive, or we're at the verge of actually seeing something. And both of these seem to be pretty exciting. One would lead to a totally new way of doing experiments if we can overcome this type of background. And the other one would even be more exciting because it means that we're actually going to detect it in the next little while. But at the moment, I think it would be a little bit premature to declare victory here.
So you're actually involved with one of the dark matter detection experiments at Snow Lab, the one called Picasso. Can you tell us what the setup is there and what you're hoping to find?
So Picasso is a rather small experiment that uses a very, very unique, very innovative way of trying to find dark matter. Mm-hmm. So Picasso, first of all, looks for what we call spin-dependent interactions. So because we don't really know what dark matter is, we have to give it some leeway in terms of how it interacts with other materials. And so there's two types of particles that we know. Some carry spin and some don't carry spin. And since we don't know anything about dark matter at this point, except that it's there and how much of it is there, we could either look for dark matter that has spin, or we could look for dark matter that doesn't have spin. And Picasso is one of the few experiments that is dedicated to looking for spin-carrying dark matter. It is a lot harder to look for spin-carrying dark matter, but there's no theoretical prejudice if the dark matter has spin or not. So it could very well be that all the large experiments that look for spin-independent interactions will come up empty-handed, while later on some of the experiments that look for spin-carrying dark matter would find something. And so Picasso is one of the few experiments that looks for spin-carrying dark matter. And what we're doing is we have a suspension of superheated freon that sits in the way of the dark matter. So in our mine, 2 kilometers on the ground, behind a water shield, we have a heated jar of jelly that contains freon. Freon is a refrigerant that could be used in your refrigerator, and it boils at negative temperatures, and at room temperature it is superheated. What that means is the liquid is still a liquid. It hasn't evaporated yet, mm-hmm. But the slightest disturbance of the liquid will cause it to boil.
Okay.
And so we suspend tiny droplets, about 200 micrometers in diameter, in this jelly. And whenever one of these droplets boils, all we hear is a pop. And so we have around our buckets of jelly we have microphones, and we pick up particle interactions that cause our bubbles to pop, or liquid droplets to pop, and turn into bubbles. We pick that up acoustically. So this is an experiment that allows us to detect particles acoustically. And that is a pretty neat way of detecting particles, we think.
So I have a question from the chat, from Terry.
What would you accept as proof that you'd identified a dark matter particle?
I would be pretty hesitant to accept anything. In reality, I would at least want to have a result that is significant, meaning statistically significant, from various different experiments with various different methods and at different locations being performed and showing the same conclusive result. I think that is probably what the only thing I would accept as real proof. And let me say why I mentioned that there are several experiments that don't really line up in terms of what they found. There is an experiment that has been running for many, many years, about 10 years, in Gran Sasso, Italy. There's an underground laboratory, not quite as deep as the one here in Canada, but still pretty deep, and a fantastic laboratory. The experiment is called Dama Libra, and they have measured what they think is a dark matter signal for many years now. But their signal is not accepted by the community. And the reason is that although they claim a very, very high statistical significance for their result, they have not answered a lot of the questions that were asked by the community in a way that has satisfied anyone. And so their result is not really taken very seriously at this point, which is a little bit sad because they have done a lot of good work, but they have just not addressed any of the questions and have not allowed anyone to look at the data or the experiment. And this has been going on so long that there's now a group in the US and Canada that is trying to recreate that experiment at the South Pole, because there you would see a distinct difference in the signal. If it would be the same signal, it would be distinctly different. If it would be the same dark matter interaction that they observed there, it would result in a distinctly different signal, and that would actually allow us to make a conclusive statement about this type of measurement. But in order to answer the question, for me to accept a dark matter result, it would really take more than one experiment, more than one location, with a really high statistical significance.
So repeatability and reoccurrence.
Yes, absolutely.
You're listening to Skeptically Speaking, and today we're on the line with Carsten Krauss, a particle physicist and associate professor of physics at the University of Alberta, and we're talking about the most recent experiments and developments in dark matter research. And we'll be right back after this.
On the next episode of Skeptically Speaking, we're looking at what the evidence has to say about common claims about diet, exercise, weight loss, and other hot health topics. We're joined by health law professor Timothy Caulfield to talk about his book, The Cure for Everything, Untangling the Twisted Messages About Health, Fitness, and Happiness. And researcher and science blogger Cy Curious looks at a new study of coffee consumption and the effect it may or may not have on life expectancy. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, guest hosting today for regular host Desiree Schell. Today we're speaking with Associate Physics Professor Carsten Krauss, a particle physicist involved in the SNOLAB Picasso experiment designed to detect the existence of dark matter, about recent developments in this mysterious area of cosmology. So I have another question from email. This one's from Patty.
We've been finding hundreds of exoplanets around other stars, and now there's speculation about planets wandering around between stars. Is it possible that these planets explain some of the missing mass?
Probably. But people have been looking for this. And if they would be rogue, that means they're not gravitationally bound to any of the stars. And so they would also probably be able to leave galaxies. And they would then obscure light from other galaxies if they would, for example, be at the very outskirts of our own galaxy. They would be blocking the light that comes in from other galaxies occasionally. People have been looking for this type of occurrence, that something that is visible but dark, in the sense that it doesn't emit any light on its own, would come across the path of some known object and ourselves. And it just hasn't happened often enough to be able to explain it. So it is quite possible that there are lots of other objects out there that we can regularly observe, but people do not believe that they account for a sizable amount of the dark matter that we're looking for.
So we have a lot of questions coming in from the chat, which is excellent. But before we get to that, I actually wanted to talk about a study that came out of Chile last month, mapping the motion of stars within 13,000 light years of the sun, with more precision than was previously available. And their data shows that rather than missing matter, they seem to have pretty much exactly what they need to account for the movement they're seeing in that particular area. What does this mean for dark matter theory, or at least dark matter in that area of our solar system?
I have to admit, I didn't actually read the paper, and one of the reasons is that I'm not an expert in astronomy, and so I probably wouldn't understand some of the intricacies of the measurement very well. But because it was very visible, this paper was very visible in the popular press, I asked one of my astronomer colleagues about this, and he said that they actually made a lot of assumptions when they did that measurement, and some of those are maybe not very well founded. And so he didn't actually believe a word of it. Okay,
so there could be some experimental errors, for lack of a better term, in this case.
Probably not even just the way that the data that they gathered was interpreted leads to that result, and I mean, you don't want to assume that they actually wanted to find that particular result, but sometimes that is what can happen. If you're not entirely honest or open about the type of assumptions that you make, it is possible that you bias the result a little bit. But then again, I am actually not in a position to make a statement about this particular paper and why they came up with that result that contradicts a lot of other findings in the same area that have not found this particular problem with dark matter.
I have another question from the chat from Distimpson.
Are there estimates about the properties of a dark matter-type particle? For instance, its mass or its speed? Or is it neutrino-like in terms of interactions?
It depends a little bit on your personal preference, what you're looking for. So there are a lot of candidates in the particle world, some theoretically very well motivated and some not that well motivated, that could make up dark matter. And so as a particle physicist, obviously I'm looking for a particle. And so that is my first prejudice, and that prejudice always goes into what I do, because if dark matter is not made by particles, I'm not going to find anything, because I'm looking for a particle. Now, we have never found anything that's not a particle in the past, but that doesn't mean that somehow dark matter could be a continuous field of some form. And then, of course, there are popular theories, and those theories are what normally everyone looks for at the moment, and that's where this WIMP comes from that was mentioned before. And so the WIMP, the weakly interacting massive particle, is just the most likely particle that fulfills all the requirements for the observational evidence that we have found. It is heavy, extremely long-lived, so that it could have been produced in the Big Bang and still be around. Mm-hmm. And it interacts only weakly, and that's why we haven't found it yet. And so the standard model of particle physics does not have such a particle. The neutrino is the closest, but it moves too fast and doesn't have enough mass. And so we need to find a theory that provides such a particle in a natural way, without breaking a lot of other things about the standard model of particle physics, which, after all, works really, really well. The theorists are not very happy with the standard model of particle physics, but that's a problem really for the theorists. because it does work so well. Right? In some sense, it's the most beautiful theory we have. Theorists don't like it because there are a lot of free parameters and a lot of complicated things that aren't beautiful, and in some sense we like beautiful theories. And so what people have come up with is what is called the supersymmetric model, and that would just provide a whole number of extra particles, all of which would be heavy and normally not observed, but there would be one particle that would be stable, heavy, slow moving, and very abundantly produced in the Big Bang, and that particle would be the dark matter that we're now looking for. But that's just one theory. One can formulate a million theories, and there's probably a million different particles that have slightly different properties than what we're looking for right now. And so it's not excluded that we're looking for something that doesn't exist, or that we're going to find something that has slightly different properties than we look for. And we're just going to find it by accident because it's not the theory that nature doesn't actually provide us with the theory that we invented. But of course we have to look for the theory that nature actually implemented.
So it sounds like part of the real challenge here is you're not entirely sure what you're looking for.
No, that's correct. And so the question, of course, asks for what do we know about this already. So I explained now what are we looking for, and what we know about it is, in some sense, very little. I mean, I listed all the requirements. Mm-hmm. It has to be stable. It has to be weakly interacting. It has to have mass. Otherwise, it wouldn't explain all the observations. But what it allows us to do, based on the dynamics of galaxies, we know how much of it has to be there, and so, and we know roughly what the most probable value for the speed of the particles would be. Because if it's too fast, it would escape from the galaxy, right? Based on gravitational laws. If it's too slow, it would all collapse into the core of the galaxy. That we haven't observed. We haven't observed that it all goes away. And so it still has to be around, and so it has to be a velocity distribution in a certain range around a central value that we know. But since we don't know how large the mass is, we don't know how large the density is. And so we know the overall energy density, but we don't know how many of them are there, and we don't know what the mass is.
So there are 3 different theoretical categories of dark matter, according to some of the things I've read, which are cold, warm, and hot. What are the differences, and could these differences help explain some of the conflicting experimental results we've seen so far?
Yeah, that would be nice. But no, I don't think it can. No. So cold dark matter is what I have just described as part of the weakly interacting massive particles that we're looking for.
Right.
Hot dark matter would be neutrinos.
Okay.
And they're basically already excluded. And warm is just something in between for people that can't make up their minds. It's really not a very favorite theory at this point, although it's not excluded that we have different types of dark matter, that some of the dark matter is actually hot, some of the dark matter, well, we know it is because we know that there are a lot of neutrinos out there. But most of it has to be cold based on the dynamics and the distribution of galaxies and dark matter in the universe. But there's actually not that much room for hot and warm dark matter. Most of it has to be cold, based on the observations that we have made.
I have another question from Ben in the chat room.
Is dark matter believed to be rather diffuse, like interstellar gas and dust, or might some of it clump together into planets or stars?
That's a fantastic question. We don't know. The short answer has to be we really don't know. In terms of simplicity, right now, when we search for dark matter, we just assume that it's completely isotropic. So very much like gas. But there's no real justification for it to be like that. Because we don't understand very well the dynamic that formed the dark matter, it could just as well be that it is actually coming in clumps. But as we haven't actually found it yet, and we don't know the properties or the dynamics very well, it's just too early to answer this question. And of course, let me also say this. If, of course, it comes in clumps, it could very well be that there's actually very little dark matter around us, and we won't find it with direct measurements for another little while. And then maybe a few billion years from now, all the dark matter will be right here, and then it would be really, really easy to find. But at this point, we don't have any strong reason why we would suspect that it is like that. So I think our assumption that it is isotropically distributed, meaning that it's very gas-like and surrounds everything around us with the same amount of density every direction we look in, is probably a good assumption.
So as we continue the search for dark matter, some people are considering that maybe we just don't fully understand how gravity works, which you mentioned earlier on in the interview, that it may work differently than our current theories tell us. Yeah, so how likely do you think that is?
That is a big stream of alternate research in terms of trying to explain dark matter. It's called modified Newtonian dynamics, or MOND, and it has had a pretty good run in terms of explaining some of the properties of what we observe, but it has never been able to explain all of it, and especially this bullet cluster that I talked about. And I would encourage everyone who's listening, if they haven't seen the bullet cluster, just to Google the picture, Google image for bullet cluster. It's a beautiful image. It's a composite image with lots of different observations that went into this picture. And this is probably what put this modified Newtonian dynamics to bed. I think there's very little active research in it right now. There are some people that are still working on some aspects of it, but I think as an overall explanation of the dark matter phenomenon, it's not the most important stream of research at the moment.
So from where you're sitting, dark matter is the better horse to bet on?
I think so.
So
well, I'm doing so.
I would hope so. So as we get more and more data, the mysteries surrounding dark matter seem to get sometimes more confusing and even more mysterious. How exciting is it for you, or perhaps frustrating is the better word, to work in this cutting-edge field?
No, I think exciting is really the right word. There are lots of new experiments coming online. It is requiring a lot of patience because if you want solid statistics, which I said is one of the requirements of accepting any new observation, if you want solid statistics and you get one event in a ton in a year, it means you probably need 5 or 6 events. Either your detector has to be incredibly large or you have to wait a long time. And usually it means you have to do both. The large detector and wait a long time.
Right.
And so it is a very exciting time. New experiments are coming online everywhere you look. But of course, it is a field that requires a lot of patience and very, very careful analysis of the data. And so often it takes years between an experiment is started and you get the result.
And finally, for those of us who are keeners like me, is there a website or a blog or a place where we can go to keep up with the latest news on the quest to find dark matter?
Depending on how deep you want to go, I would think that the dark matter conferences like the IDM that's happening in Chicago in July this year, so I'm sure there will be a lot of interesting results presented there. And last year we had the Tau-P in Munich. There were a lot of interesting results presented there as well, and all those presentations are online and can be directly looked at. So that will be a Tau-P, TIUP 2011 for those talks that are already online.
Carsten, thank you so much for being here with us today. It's been a pleasure.
Thank you.
If you want to learn more about dark matter and the people and experiments searching for it, you can visit the SNOLAB website at snowlab.ca or check out picassoexperiment.ca. All of these links and a link to Carsten Krauss's website will be available for clicking in our show notes on skepticallyspeaking.com. If you'd like to keep up with Skeptically Speaking, you can follow us on Twitter at Skeptical Radio, visit our Facebook page, or check out our Google Plus feed for all the latest news and updates. You can also visit Skeptically Speaking on iTunes, where you can subscribe to the show, download all of our past episodes, or leave a review. Thanks for listening to Skeptically Speaking.
I wanted to use just a wee bit of this episode to talk to David Grelli, the treasurer of the Edmonton New Technology Society, because I love it. Welcome, David.
Thanks for having me.
So what is ENTS?
We like to refer to ENTS as a collaborative workspace. We have about 4,400 square feet worth of space where we put a lot of really passionate and creative people in the same room with tools and all sorts of inspiration from other spaces. And the general theory is that when we do that, interesting things and fun things are going to happen.
So what kinds of things are done there then?
It really depends it's up to the individual members what happens. We call ourselves member driven in the sense that we don't have any sort of planned programming. We have members who have done everything from built 3D printers, which seems to be a very new and accessible technology. It used to be a $40,000 or $50,000 investment. Now you can get into that as a hobbyist for about $1,000, $1,500. We've had more than a few members who've gotten into 3D printing that way. We have another member who is electrifying a moped because he wanted to build his own electric bike that way. It's really up to the member that comes in as to what happens in our space.
Now, and this isn't the only space of its kind, is it?
No, we're definitely not the first. It originally started, I believe, in Germany. There's a couple of spaces that opened up there, and it's spread out from there. There's about, I want to say, close to a dozen across Canada, many in the States, and it covers most of the world at this point.
So this is, honestly, it's kind of like a geeky play space for adults.
When I first started describing it, it was like the Foot Clan lair in the first Ninja Turtles movie, but for geeks.
Okay, honestly, that's perfect. Thank you.
It's a clubhouse, right? That's effectively what it is. It's a clubhouse for people who like having very expensive toys and don't always have either the ability to buy them themselves or the space to run them. One of our directors was told that he wasn't allowed to keep his motorized metal mill in the kitchen by his girlfriend.
He has found a home. That's lovely.
It's true. Yeah.
So you mentioned there were other spaces like this. Where are they in Canada?
In Canada, I mean, there's one in Nelson, BC called the Nelson Tech Club. There's Protospace in Calgary, Skull Space in Winnipeg, Ohm Base in Thunder Bay, and Art Engine in Ottawa. There are numerous ones that pop up that I'm sure we haven't even heard of yet. It takes quite a while to get a space up and running and build the community. So there have been attempts in Grand Prairie and other cities, and they sort of falter at first, but eventually they find their footing and they take off.
Well, if you had any advice for people who are trying to start hacker spaces, what would you say?
That's something actually we ask ourselves quite often because we always feel like we're rebuilding and reinventing ourselves and almost restarting every few months. Not that we disappear, just we try and make sure that we're not missing anything. Advice to someone trying to start a space would be reach out to other spaces. They're all very, very active online on IRC and email lists and web forums. Reach out to other spaces, talk to the directors, and find out what has worked for them, what hasn't worked for them, but also be willing to adapt it to your specific community. There is no one-size-fits-all with the hackerspace movement.
Well, speaking of specific community, for our local listeners, they can actually come to see the Edmonton New Technology Society for themselves, can't they?
Yeah, they can. We have a standing event that we call Hack Tuesday. Generally, it starts usually 5 or 6-ish after most people get off work. It runs till the wee hours in the morning. It's always open for anyone to come by and visit. We also have a general monthly meeting first Sunday of every month. That again, the public is more than welcome to come check us out.
And where can people go for more information?
Check our website. It's www.ents.ca.
Thanks very much for being here, David.
Yep, not a problem. Thanks for having us.
And we've added a link to ENTS on our website at skepticallyspeaking.com. Thanks for listening, and we'll see you next week on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.
Skeptically Speaking is produced with the support of CJSR 88.5 FM in Edmonton, Alberta, Canada. Our studio assistants are Brent Kelly and Rachelle Saunders. Ryan Bromsgrove is our studio technician and research assistant. The show is produced and edited by K.O. Myers. Our theme song was written and recorded by A.O.K. And I'm your host, Desiree Schell.